Welcome back, everyone. In this video, we're going to start creating our training function, which is going to be a long one, so it's going to span across multiple videos. So, define training function. It's going to take some args. I'm going to scroll down, and then we're going to set the seed to ensure that it's reproducible, set underscore seed, and that is going to come from args.seed because we're going to be passing in a bunch of arguments, and one of them is going to be the seed. Okay, now the data set. Load from disk. We discussed what this function does when we imported it. It loads a processed data set saved locally at the args.dataset path, and this is our tokenized text data set ready for casual language modeling, okay? Now, here we load the model from the hub with a BNB config, okay? So first, let's define the BNB config, which is the bytes library that we imported. So BNB config is going to be equal to bits and bytes config. And now we're going to say load in underscore 4-bit. It's going to be equal to true. And this will load the model in 4-bit precision instead of the full 16 or 32-bit precision. And this actually replaces the standard linear layers with bnb.nn.linear 4-bit layers, which is why we can look for these layers in the find all linear names. So if we look, if we come back over here, remember how I told you not to worry about bnb.nn.linear 4-bit? Well, now we understand why. So when we're looping over the modules, and if a module has an instant of bnb.nn.linear 4-bit, we know that it can be and it will be a LoRa layer, okay? And that's because this code over here, load in 4-bit, converts the standard linear layers with this specific layer type, okay? So that's why in this function, we're going to be able to look for bnb.nn.linear 4-bit, okay? When we look for the linear layers, which can be used with LoRa, okay? And obviously, this is going to run first. And that's why we're going to be able to have access to this in this function, okay? So I hope that makes sense. So we load in 4-bit, which is true. Now I'm going to say bnb underscore 4-bit underscore use underscore double underscore quant is going to be equal to true. And we're going to apply double quantization to compress the weights even more. In the previous video, we talked a lot about double quantization. So if you feel like you don't understand it, please refer to the original video, which we just did one video earlier where we talked about what double quantization is. Okay, and over here, we're just going to say that, yes, we use it. Now I'm going to say bnb underscore 4-bit underscore quant underscore type is going to be equal to nf4. And so this specifies the quantization format to use for converting full precision weights into 4-bit values. NF4 stands for normal float 4-bit, which is a custom 4-bit floating point format introduced by the bits and bytes library, and it mimics the distribution of normal float values, meaning it handles small and large numbers better than the standard int4. And so it improves quantization accuracy, especially for transformer weights that follow a roughly Gaussian distribution, okay? So over here, we're not going to say to use int4, we say use nf4, which is similar to int4, that it's 4-bit, but it was custom made for these kinds of tasks, okay? So it's a lot more accurate. And now I'm going to say bnb underscore 4-bit underscore compute underscore d type, and that's going to be equal to torch dot, oops, what's happening? Oh, we didn't have a comma there. And so this is going to be equal to torch dot bfloat16. And so this specifies the precision used for computation, example matrix multiplication, after the weights have been dequantized from 4 bits. Remember, our model weights are stored in 4-bit NF4 for memory savings, but before computing, for example, the forward pass, they get dequantized for a higher precision type. And this line tells the model to do all the math, example, the attention layers, layer norms, activations in bfloat16 precision. And when I say that the weights get dequantized, it means that they're reconstructed using the scale parameters that we discussed previously. Okay, so essentially this just tells the model what to do the calculations in. And now we can say model is going to be equal to auto model for casual LM dot from underscore pre-trained. Okay, so this loads a pre-trained casual language model that is used for text generation. And obviously, casual LM means each token is predicted based on the previous ones. So it's a decoder only, similar to ChatGPT or Mistral, the one that we're fine-tuning now. And we're going to say that the args dot model underscore ID. So this is the first parameter. This is the ID of the model that we will use. Use underscore cache is going to be equal to false. And we're using gradient checkpointing, so we must disable the cache to save memory. Now I'm going to say if args dot gradient checkpointing else true. So over here, what we're saying is, actually we don't need this comma over here. So we're saying that use cache is going to be equal to false if args.gradient checkpointing is true. Else, use cache would be true. Okay, I know this is kind of like a one-liner in Python, but it's actually quite logical to read it. So, use cache is going to be false if args.gradient checkpointing is enabled, and for us it's enabled. Okay, so that's why use cache is false. Else, if this is not enabled, then the value of use cache is true. Okay, so this is just some nice Pythonic way to write this. Device underscore map is going to be equal to auto. Now what is this? Well, this means it automatically spreads the model across available devices. Example, multiple GPUs or GPU plus CPU. So that's what we're doing over here. And quantization config is going to be equal to bnb underscore config. So this will apply the 4-bit quantization config we created earlier here at the top. And now our model is ready to go. It's going to be loaded with these informations. Awesome. And now let's say that the model is going to be equal to create underscore PeFT underscore model. And that's going to take model gradient underscore checkpointing. It's going to be equal to args dot gradient underscore checkpointing, and bf16 is going to be equal to args dot bf16. So over here, this is the create PeFT model, is the function that we created over here. Okay, it actually takes in a model and we add stuff to it, right? We add the LoRa config to it, we enable mixed precision training, so that's essentially what we're doing. And now we have our model. Now let us define the training args, not the training args, sorry, the first, let's define the directory where the train model and the logs will be saved. So we need an output underscore dir, which is going to be equal to, I'm going to say /tmp/mixroll. Awesome. And now in the, actually, let's continue because we have a lot more in this function. So now let's define the training args and the Hugging Face training arguments. So training underscore args is going to be equal to training arguments. And now we're going to say output dir is equal to output dir per underscore device underscore train underscore batch underscore size. And that is going to be equal to, I'm going to copy this, and I'm going to say args.this. Awesome. Now bf16 is going to be equal to args.bf16. So use bf16 if available. Learning rate is going to be equal to args.lr. I know this is super tedious. Sorry, everyone, but we also have to do this. Number of train epochs is going to be equal to args.epochs. Nice. Gradient underscore checkpointing is going to be equal to args dot, and I'm going to copy this, args dot gradient checkpointing. And now we're going to say the logging underscore directory is going to be using f string, and we're going to say output underscore dir, and we're not done yet because we want the logs to be in the /logs, like so. Now the logging underscore strategy is going to be equal to steps. So log every 10 steps. So not epochs. So we log like every 10th batch. Okay, because we're going to say that the logging steps is equal to 10. And now we're going to say save strategy is going to be equal to no. We disable automatic checkpoint saving. If training crashes, we restart, which is kind of a pain. So this is probably one of the few differences in production. You would probably want to have a saving strategy, but it takes up more memory, and that would cost us a lot more money. So right now, we're basically saying if the training crashes, we're going to have to restart. Okay? And now we're going to say that the trainer is going to be equal to the trainer. Oops. And we're going to say the model is equal to the model. Why do we have so much? Okay, we closed this. Okay, so model equals model. Then we're going to say that the args is going to be equal to training underscore args. Nice. And then we're going to say that the train underscore dataset is going to be equal to the dataset. And we're going to say data underscore collator is going to be equal to the default underscore data collator, which we imported at the top, and this will basically just batch the data for us automatically. Okay, and actually we finally got to the point where we can say trainer.train. Obviously, we're not training yet, but here is where we actually call the train function. And now I'm going to stop the video because we're not done with the function yet, because we haven't decided what happens when we save the model, how we save it. So I will see you in the next video where we finish the training function.